Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
let's start doing a few more examples of the method of moments and maximum likelihood for finding estimators. I think it's a natural one to do the gamma parameters A and B. X, we'll do an I sample once again, xi, or ib, gamma. And let's do the method of moments first. Let's get a bit more of a feel of how these work. We have to remember that the theoretical moments first. Expected value is AB. We calculated this before. Is AB squared, BB is scale parameter. And we don't use the variance per se, we use the second law moment. So expected value of xi squared, the second law moment is a b squared variance plus the mean squared. B squared. And so we set, to do the method of moment, we set the sample mean, really we'll solve these for A hat and B hat. And we often call this M2 prime, the actual observed second moment, observed second sample moment. As a reminder, that is the same as you get for x bar except when you square the variables of one over n, so y equals 1 to n of x squared. In terms of the consistency, the fact that we use 1 over n rather than 1 over n minus 1 does not make any difference because consistency is a large n property, so n tends to infinity. Yeah, it'll turn out as usual that the method of moment estimators are consistent. But often we want something more than that. Often we want unbiased, and we'll see that's not always the case. So, unrelated. Let's solve these for A and B. I guess an easy way to, so we have two equations and two unknowns. And we want to, let's eliminate B by saying that B is equal to x bar divided by A. Many ways we could do this. And as a reminder, A and B are positive in the definition of a gamma, otherwise you get a degenerate distribution. So we can assume A and B are positive. Substitute that in, M2 prime equals x bar squared, A plus A squared divided by A squared, so that's 1 over A plus 1. M2 prime minus x bar squared equals x bar squared divided by A. So ultimately the solution we find for A of the A hat is x bar squared M2 prime minus x bar squared, and B is x bar divided by A. So that's M2 prime minus x bar squared. But there's no longer a square because that's cancelled out. Now, sometimes it's nice to do these in terms of the sample mean and sample variance, just because those are parameters you might have calculated. It's worth noting that M2 prime minus x bar squared, that's just equal to 1 over n of some xi squared minus n x bar. That's another way of saying it. So that probably looks like a familiar formula, except it has n in the denominator rather than n minus 1. So as usual, another way to write this is that it's a normal sample variance, except the version that has n in the denominator instead of n minus 1. So I could write this the following way: x bar squared divided by s squared, except it's actually n minus 1 over n squared. So put that factor out as well. And similarly, I could also do the same thing here. N minus 1 over n s squared. So all of those things are straight to the same. That's one way of comparison. The method of moments in the case where you know how to do the true moments is often quite quick. So maximum likelihood, depending on how good you are at differentiating, can sometimes be a bit slower, but let's check it. And it has more general application, which we'll see in a moment. So let's check the maximum likelihood method in this case. Recall, okay, now this is a general recall for likelihood. The likelihood function. And this is actually going to be a little bit more general than what we saw. L of, let's just say, x likelihood of the parameters, in this particular context, A, comma, B. Now, the semicolon means after this it's just the observations, which we don't let the observations vary, we just take them as given. Given x1, x2 up to xn is equal to the joint PDF. Now, in this case it's a PDF because gamma variables are continuous. If it was discrete observations, we'd say the joint PDF of x1 up to xn given parameters A and B. Now, in this case, we're doing it for, as I said at the start, our example is, that we're talking about, example 1 is xi that are IID gamma. And because we're doing that example, it's easy to think that this is just going to be a product. It is in the IID case. But in the general case, you might not have an IID sample. There's some ways you could do that. You could say the second one depends on the first. You could have sampling without replacement. You could have some kind of complicated chain thing. All I'm saying is that the maximum likelihood applies to all these situations, no matter how complicated. You just, so long as you can come up with a joint PDF or joint PMF, that will be your likelihood function. So it's very good for dependent sampling. So in this, okay, so in, and you could have any number of parameters. Normally we'll only do 1 or 2. Okay, so going back to example 1, likelihood of A, B, given, I'll abbreviate it by writing all the x's in one go, is product I equals 1 to n. Because of the IID, all the xi's are independent, so I take the product of their marginal PDFs. Joint is the product of marginals when it's IID. And now I have to substitute as a basic step, that's fxi of xi. Now all those are the same function, go at a different point. And I'll just put brackets a comma b here because there's no clear way of denoting the marginal density function. It does depend on the parameters, so I've just put the dependence there. So that is product I equals 1 to n. Now I have to recall our gamma density is x I to the power a minus 1. A is that number, even minus b x I divided by gamma of a b to the power. Now the bottom part doesn't depend on it, so I can put that out front. 1 over a b to the power a, all of that can be to the power n. The rest of the stuff is different for different i's. So I've taken a constant out in front. The product of the xi's equals 1 to n. I'm going to do these two factors separately. First of all, I have the xi's all to the power a minus 1. Now, it will be a bit simpler if I put, if I have each individual xi to the a minus 1, that's the same as the product of the power a minus 1. This will be a bit simpler because I'm going to differentiate with respect to a. So just make whatever simplifications you can. And similarly, when I'm producting e to a whole lot of different exponents, I add the exponents. So e to the power minus b sum I equals 1 to n xi. So that's a nice function of two variables. And Thank you. That's very important. Yeah. There's a B convention and a lambda convention. The lambda convention is the rate parameter we get in front of it. Thank you for the correction. Right. So let's say that's e to the power minus b formula for the natural log. So for the maximizing, we search for a point, as before, with dl A and dl B. The two parameters both have to be zero, because when you're finding maximum likelihood estimates of two parameters at once, you have to maximize the function of two variables. So let's do those two partial derivatives. dl dA equals to well, having a gamma of A makes it a little more complicated. So minus n over gamma A. Oh, that's right, gamma prime of A, that's some function. Minus, this is differentiated with respect to A, I'll just get n of B. And then this one, A minus 1, once again I'll get the coefficient of that plus log of product of dxi. And then the final term, there is no A involved in the final term, so I'll leave it at 0. So we'll be setting that to 0. And we'll also be setting dl by b to 0. dl by b, there's no b involved in this there. There's here I'll have minus a and b. I'll have no b involved in that term. And then that will become plus 1 over b squared. Sum I equals 1 to n of xi. As always, x's are treated as constant when we do the partial differentiation. So in the end, the second one of these looks more simple to solve, to get some relation from, because there's only two terms. That will tell me that b hat, whatever b hat is, when I solve for that, it will have to be sum I equals 1 to n of the xi's divided by a n. If you're just imagining setting that whole thing to 0, I get b a n equals sum of xi. So another way to write that is, and I should make that an a hat as well. So b hat, a quick way to write that is b hat equals x bar divided by a hat. Now let's just compare. So at least that relation between b hat and a hat is the same as we got in the method of moments. So you just see it's been a bit more laborious to get to this point. And then let's try substituting that into the first equation, which will be true at the same time, and see if we can get a. So substitute into EL EA equals 0. We get 0 equals minus n. There's still this logarithmic derivative of gamma prime of A over gamma of A. Minus n log. So I can substitute in this b that's been observed, x bar divided by a. All of this is at the point a hat plus log sum I equals 1 to n xi. Now, this, if you think about it, we're trying to solve, so we've substituted everything we know about b into the first equation for a. This looks quite difficult to solve for a, so the only, because if it were just kind of linear in a or something like that, we'd know how to tease it around to solve it. Here we've got something involving the gamma function, so the only hope is if we can find some relation involving the gamma function. I'll just remind, there is this definition of the gamma function which you would recall because it's it's just the density that integrates to 1 u to the a minus 1 e to the minus u du from 0 to infinity. If you put gamma of a on the bottom, that integrates to 1. So this is a definition of the gamma function. If we differentiate under the integral sign, gamma prime of a, now normally you should check whether that's valid or not, but here let's just do it. it's bounded enough for this to make sense. So I'll get, I'm differentiating with respect to the exponent, not with respect to the denominator. So that's u to the a minus 1, that's e to the power a minus 1 log u. So let's write it this way, d by dA of e to the power a minus 1 log u, and then minus u. So that's equal to integral from 0 to infinity. If I put the a derivative of that, the a derivative of that is just log u. So by the chain rule, I get e to the power a minus 1 log u minus u. That's what happens when I just replace this by d by dA with the same thing. Now, I can put it in the same form as before, u to the power a minus 1 e to the minus u du. Okay, so basically this seems like a pretty intractable integral. So I'm going to rest it there. The conclusion is we haven't been able to find the maximum likelihood estimator using this method because the derivative is just too complicated. We can't find we can't solve for the solution a hat and b hat. We did find the relation between b hat and a hat, which is this, but as far as it's reasonable to expect there would be a unique solution of that, you can check that using its derivative properties. Like if that's always increasing, then there's going to be a unique solution, but as to actually finding that solution could be quite difficult. So that's one case where the method of moments really wins out because you can solve it quite easily. So we'll just leave that for now. Let's now do a maximum likelihood estimator for another example that we talked about earlier. Example 2. We did talk about this this is still going to be an IID case, x1 up to xn, which are IID uniform from 0 to theta. Now we talked about various estimators for this, but I don't think we actually derived the maximum likelihood estimator. So let's derive the maximum likelihood. We did the method of moments estimators. You remember it was x bar divided by 2. No, it couldn't have been. No, it was 2x bar. 2x bar. Because, yeah, if you have uniform 0 to theta, each of them has expectation theta over 2, and then you just double x bar and you get an unbiased estimator. So to recall that, the method of moments estimate was a not particularly efficient estimator, but a phi hat method of moments equals x bar times 2. Okay, and that's unbiased. So now let's do maximum likelihood estimate for this thing. So we have to write down the likelihood function, and this is where some attention to boundaries and details will help you a lot. So let's say the likelihood function of, once again, the unknown parameter theta given the observations x1 up to xn. Okay, so for short, likelihood of theta given the vector x. And what is that? That's the product. They're still IID, so it's still product I equals 1 to n, the density of xi, and then reminder that there's a dependency on the parameter theta. Now we remember the density of a uniform is 1 over theta. That's quite easy. But let's be a bit more precise about it. It's 1 over theta indicator function. See, this indicator function is sometimes a very good way of expressing a limited range. Because the density of a uniform from 0 to theta, it's not constant on the whole real line. It's only constant on the interval where it's allowed to lie. So a good way to write that density is 1 over theta, in order to have the area 1, times indicator function that 0 is less than x less than theta. If you're worried about whether we include 0 or theta, it doesn't matter because of continuous random variables. It doesn't land there anyway. So indicator function that 0 is less than x less than theta, and that would be xi in this case. So this is just a function that is 1 if that's in that range and 0 otherwise. And I have to product, of course, I equals 1 to n. Now, if I put together all those n, it will be 1 over theta to the n, but of course there's also a constraint, indicator function, that it's the product of all these indicator functions. Now, if you're saying 1 if this event is true times 1 if another event is true times another one, when you multiply indicator functions, that's the same as the intersection of the events. So all of these have to be true at once. 0 less than x1 and x2 and x3. All of them have to be in the range, xn, all of them have to be in the range 0 to theta. Because if any one of them was not in the range 0 to theta, then the corresponding number here would be 0. So the likelihood is only positive if all of the numbers x1 up to xn are in the correct range. Now this is one, having recommended the log likelihood function very highly, that's really only a great idea when you've got a big set of, it can confuse you. So I'm not going to take the log likelihood function here because frequently the log likelihood function would be log of 0, which is minus infinity. So that can be confusing. So let's just maximize L without going to the log, because it would be easy to think, okay, it's 1 over theta to the power n, and it's L as a function of theta. So if I make theta bigger, then 1 over theta to the n gets smaller. So it's easier to think I just have to make theta as small as possible. And what is the smallest theta you could have? 0, I guess. So that would be a wrong but easy trick to fall into. So as 1 over theta to the n is decreasing, shouldn't we choose theta hat equals 0? Because theta can be anything from 0 up to infinity, and then it's, you know, this thing is decreasing in theta, so I just want to pick the maximal thing. Shouldn't I just make it theta as small as possible? So that's actually not the correct answer, but can anyone tell me something that I've missed in that reasoning?
Because if theta is less than any of the x, we will get the total result.
Yeah, yes, exactly. Because if theta is less than xi for any xi at all, if there's even one of the variables that theta is less than, then the corresponding marginal density, remember we producted all the marginal, we multiplied all the marginal densities. Density is 1 over theta, indicator function that xi is less than theta, but since theta is less than xi, that is equal to 0. Okay, so that's clearly not a maximum. This likelihood is non-zero when theta is bigger than that. Okay, and so L does not achieve a maximum for theta less than. So if theta is less than any of them, then it's no good. So it does not achieve a maximum for theta less than maximum of x1, x2, up to xn. Using the same notation for order statistics, you could call that x parentheses n. That's kind of a shorthand. So thus, L of theta is here. So we can actually be a more precise statement about what the likelihood function is. It's 0 if theta is less than the maximum, which I'll just write x parentheses n, and it is equal to 1 over theta to the n if theta is greater than the maximum, let's say greater than or equal to the maximum. So you start to think that, oh, maybe it did matter that there's a less than versus less than or equal to. Well, this will be convenient for us. So let's just draw that function. The likelihood function is actually 0. So contrary to my little sketch here, there's actually a cutoff. Okay, so that sketch was not taken into account. There's a cutoff, and here is x parentheses n, which is the highest one. You have x1, x3, x4, whatever. You have all these numbers, and then xn is the highest one. And so the likelihood function as a function of theta, this is the theta axis, L of theta, likelihood function has a big jump up to here. and then it decreases. It's like decreases like 1 over theta here. So that's exactly what it is. So clearly, max of L of theta occurs at a unique place, theta hat equals x, parentheses n. Now, there might be some objections from people who are worrying about the jump, whether it's actually, you know, because I said the density is indicator less than theta. If I change that to less than or equal to theta, it seems like it would change this to make that less than or equal to and that greater than, and so I wouldn't have an actual maximum. That's kind of not a real issue, because even if that weren't a solid included point there, it doesn't matter. The maximum still occurs there. If you don't like the idea of maximum, you could just say you approach the maximum. So I would encourage you still not to worry about exact issues of less than versus less than or equal to. Regardless of which way you choose it, it's clear that the maximum of the likelihood occurs pretty much at this point, because that's the highest you can be. It's 0 here, and it's decreasing to the right. Okay. So theta hat MLE is, of course, x n, the nth observation. Now, that's the estimator. Now, it's not unbiased. We found that before. Expected value of x n is actually n over n plus 1 times theta. That's for a fixed theta, we found that. So one way to get a unbiased estimate, which we already talked about, that was more efficient, was just to sort of observe that and say, oh, if I multiply by n plus 1 over n, that's a new estimator which is unbiased. And that we did that and we calculated the efficiency of that. By the way, there was a little error when I was doing that live. Efficiency of theta let's say that one is theta tilde. Theta tilde with respect to theta hat MON was, we did a calculation, it is actually more efficient. The formula was n plus 2 over 3. Anyway, so I've corrected the notes on that if you check through the PDF file. That's the exact efficiency. So interestingly, when n equals 1, the efficiency is 1. So they're actually the same estimator when n equals 1. Because when n equals 1, you take the maximum of one observation, which is just the number itself, and then you do times 2 over 1, so it's 2 times the number. But they differ for higher values of n. And the maximum likelihood is not unbiased, so that's not very good. You saw the maximum likelihood one is not unbiased, but a slight modification of the maximum likelihood is unbiased. So that's what a kind of custom way to find unbiased estimators. I want to find to talk about a general way to find. So it's even got a name. This is kind of an MVUEs, which is an acronym for minimum variance unbiased estimators. When we were talking about efficiency, of course, the highest efficiency is the smallest variance. So this is saying the most efficient unbiased estimators that you can come up with. But in order to do that, we have to talk about something called a sufficient statistic. So, and perhaps, despite the fact this course is about statistics, perhaps you're not super clear on what the definition of a statistic is. So, probably reiterating, but a statistic from a sample, and it doesn't really have to be IID, but we'll focus on the IID case, x1 up to xn, is a function g of, so it's just any function of the observations can be called a statistic that does, so long as it does not depend on any unknown parameters. So unlike in chapter 8 when we were talking about pivotal quantities, now a pivotal quantities is typically not a statistic because it folds the unknown quantity into it and then gets a known distribution. Whereas a statistic is just when you might not know the distribution of the statistic, but it does not depend on any unknown parameters. Okay, so that's the definition of a statistic. The definition of a sufficient statistic sufficient statistic U for an unknown parameter theta. Now you could do it for multiple parameters, I'll just state the one parameter case. So sufficient statistic is a statistic, so referring back to the previous definition, in other words, you can't actually know what U is. You can't actually know what theta is. It just has to be something based on the observations that is your best guess at, well, it contains all the information you need to find out about U, such that the conditional distribution of all the observations up to xn given U. So by the way, U, because it's a statistic, U can be written as some function of the x1 up to xn. And as we'll see, the best example of this is the mean, so we'll do that as a special example. Is a statistic such that the conditional distribution of x1 up to xn given U does not depend on theta. Okay. Now I'll just give some examples of this. Number one. Example one is that, let's just, I'm actually going to call this example 2 as above. We've got x1 up to xn, our IID, uniform 0 to theta, uniform 0 to theta, and we've noticed that x brackets n was the maximum likelihood estimator. U equals xn is a sufficient statistic because, we have to talk about conditional distribution. Let's talk about conditional density. Well, the joint density, x1 up to xn, given the largest one. Actually, it's a bit hard to write that as a joint density. So, let me not go into the reason right now. I'm going to give another characterization, and but before we do that, let's do an example that's easier to work with. The x1 up to xn are going to be IID normal mu1. Now, I'm just doing this with constant variance equals 1, and that'll make it easier because now I'm only talking about one unknown parameter that the variance is known to be 1. Then the joint density of x1 up to xn of x1 up to xn given the so before I do that example, I'm just going to, it's much easier if I do this following theorem. So a statistic U is sufficient for theta if and only if the likelihood factorizes in the following fashion. L of likelihood of theta given x factorizes as follows. L of theta given x equals, so you've got to be able to divide it into two things that relate. First of all, some function of theta and the statistic times some other function of statistic and the observations. So if you can factorize the likelihood into something that only relates the parameter to the sufficient statistic and something that only relates the sufficient statistic to the observation, then you have a sufficient statistic. And that's if and only if. So that's if and only if. Okay. So that theorem will make it a lot easier to do this. So let's... so the likelihood of theta given x. As you remember, the likelihood is the same as the joint density, depending on the parameter theta. So we're going to apply this theorem to check what is a sufficient statistic here. So that is e to the minus, product I equals 1 to n, e to the minus a half xi. Remember, there is an unknown mean. It's a half xi minus mu squared divided by root 2 pi. I don't have to worry about sigma because sigma equals 1. So that is equal to 2 pi to the minus n over 2. Then I have all this product of e to the minus, so that's, I'll just write x of minus a half sum I equals 1 to n of xi minus mu squared. Now there is this great observation that we've made in many other contexts, which is that when you have sum of xi minus mu squared, you can break that up into xi minus x bar and then x bar minus mu, and you get no cross term when you do that, minus n over 2. So you can check the algebra. That's the same as exponential of minus a half sum I equals 1 to n of xi minus x bar squared, and then obviously there would then be the plus x bar minus mu squared plus 2 times xi minus x bar minus mu. Because all the xi, the key fact is sum I equals 1 to n of xi minus x bar equals 0. Using that key fact, you can say that the cross term equals 0, and then just times exponential of minus 1/2 of sum of x bar minus mu. So 1/2 n x bar minus mu squared. And that, so the statement that's being made here is that x bar is sufficient for mu. Okay? So to check that x bar is sufficient for mu, all that we've done is we've written the likelihood and we've seen that it factorizes. The 2 pi to the minus n over 2, well, that doesn't even depend on anything, that's just a constant. This guy depends on the observations and the sufficient statistic x bar. And this guy depends on sufficient statistic x bar and the unknown parameter mu. But there's no other entanglement. So sufficient statistic is a way to disentangle the unknown parameter from the observations by so the sufficient statistic relates to the parameter and the sufficient statistic relates to the observations. But once you know the sufficient statistic, so let's think about it this way. Once you know x bar, there's no longer any purpose in knowing mu if you just want to know the distribution of the xi's. Because if you know x bar, then this is all that matters. That's just a constant. So that's the meaning of sufficiency. So that was the first thing. And then you can do example 2 as above before. Let's just try it with that likelihood. Getting back to the likelihood that we saw. U equals xn is a sufficient statistic. L of theta given x is equal to 1 over theta to the n. So that depends on theta and then indicator that xn is less than theta. So that, xn is u. So this guy depends, in fact, it's kind of it's a trivial case because this depends only on u and theta, and then, you just multiply by 1, which that 1 depends only on theta on u and the observations x. So this is a funny case with the uniforms because there's actually nothing that depends on the xi's themselves. There's, that's just because there's so it still satisfies the condition in this theorem. So finally, I'm going to state this theorem called the Rao-Blackwell theorem. And the reason, well, there are many reasons that sufficient statistics are important, but this is an example which systematizes, as I said at the start, systematizes the procedure to find a minimum variance unbiased estimator. So if, let's say, U is an unbiased estimator of, I've been using for use of sufficient statistics. So I'm going to call my theta hat is an unbiased estimator of theta, and U is a sufficient statistic for theta, then so because theta hat is unbiased, I can compare it with efficiency, comparing the variance. So V, which is defined to be the conditional expectation of theta hat given U. Remember, sufficient statistics don't have to be unbiased. In fact, they don't have to be good estimators at all. They just have to summarize something. So although x bar is a sufficient statistic, n times x bar is also a sufficient statistic. It's just, sufficient statistic is just about information. So V is an unbiased estimator, that is at least as efficient